So, as we said, we're going to cover this in two parts. I'm first going to talk a little bit about performance and some performance work that we've been doing, improvements that we've been making, and some things that fall out of that. That then leads on to Nick trying to explain why the performance bottlenecks we see actually occur. So to begin with, I don't think this is going to be news to everyone or anyone. Right? When you do performance engineering, you start off with getting yourself a benchmark, preferably one that's vaguely like the workloads you're actually going to get for your application, whether that's a production server or it's a client app. Once you've got your benchmark, you analyze it to work out where the bottlenecks are. You modify just one thing, you run it again, you make sure you fixed it, and then you go on to the next problem. So it's a cyclic, iterative process. Now, for Swift at the moment, there's actually really only one set of benchmarks, which is Swift Bench. This is part of the Swift project inside the Apple repo. We've started working on something called the benchmarks game. So there's a group called Alioth. They do benchmarks actually on Linux, but they run on 4 CPU machines, and they implement algorithms. So really simple stuff like the Mandelbrot fractals, N-body, which is calculating planet locations, and they do some stuff on DNA sequencing and that sort of stuff. But it's really computational tasks. And they do it across every single language. So you get to compare how you're doing against other languages. And we found that really useful because when we started to bring libdispatch to Linux, we allowed us to go from a single-threaded, single CPU solution to multiple CPUs. So we saw how well we were spreading over the CPUs and how well we were comparing against other languages. Above that, so because we work on a web framework for Swift, we're looking at a bunch of benchmarks called Tech and Power. These do really simple web framework benchmarks. So Hello World, where you fetch Hello World from a database, CRUD update operations, that sort of stuff. And then we've got another one called Acme Air, which is actually designed to be a full microservices benchmark. So we've been running these benchmarks at every level and doing analysis for a number of months. And when we do the analysis, we do them on both platforms. So we use instruments on Darwin, on macOS, like I'm sure everyone here does. And on Linux, we use something called OProfiler. They both work in the same way. They do CPU sampling. So basically, it does a processor interrupt every period of time and says, what's the processor currently doing? That's what must be taking all the time in my application. They both work in the same way. It's just Instruments isn't great at looking into the Swift runtime itself. You have to build your own debug version of the Swift runtime to get the symbols. OProfiler kind of gets that out of the box, which is kind of nice. So we do a little bit more on Linux than we do on Darwin at some points. So what we've managed to do by taking this approach is for our server-side web framework, Kitora, at version 0.10, we were getting around 22,000 requests per second through the system doing Hello World. So the first thing we did was, by looking at instruments, actually, we found out we weren't buffering our network responses particularly well. There was a lot of time spent in our network response code, so we added some buffering. We went up to about 28,000. We did some more work, largely around code refactoring. So this was kind of a key one, and it'll be reflected in the data you're going to see. I guess most people here have been told that value types are better than reference types when it comes to garbage collection overhead and ARC counting. No? Okay. But we did a lot of code refactoring based on some rules that Apple have been talking about that are starting to get published, and some data that we saw. After that, we found a converter bottleneck in Foundation itself. So we worked around it whilst we got the fix into the open source community. Then we actually lost a little bit of performance because we couldn't use whole module optimization anymore, which has the effect of removing some dynamic dispatch. And that's going to be key, and Nick will talk about that as well. And then we implemented Keep Alive, and that gave us another boost. And so we've been incrementally working through all of these benchmarks, doing analysis, and trying to feed back code fixes to the community and to our own framework. And we've now got to the point that we're faster than Express.js, so we're faster than Node. And ZWoo is slightly faster than this. Vapor, one of the other Swift frameworks, is a fair bit slower. So this probably isn't that interesting because it's just the work that we've been doing, but hopefully this is. Now, it's a very complicated chart, but hopefully I'll be able to explain it fairly simply. This is the simple Swift benchmark results. So we're running the Swift benchmark that comes as part of the Swift project, and these are really micro benchmarks, right? They almost hit one set of APIs or a programming construct repeatedly to find how it performs. And normally you'd only do this for regression testing. But what we did was we broke down how much of the CPU time in each of these tests is spent in each of the runtime libraries. And the key bit is red is libswift core. So this is actually running the real underlying Swift code. So we saw things like linked list processing spends a huge amount of time in libswift core and not a lot of time running the application itself, which is in blue. So there's a huge framework in Swift overhead to running the linked list benchmark. And there is for a whole number of other ones as well. So we wanted to go and see what that overhead was. So the first thing we did was we looked at what comes out, and this is the functions which are being executed. And you'll see for linked list that almost, 92% of the time is in Swift retain and Swift release. And this is reference counting, right? This is adding and removing references. And that's unsurprising because you've got a linked list and you're traversing up and down the linked list to find objects. So you're adding and removing references. But where you're using reference types and you're using them to a large degree, you can have very large reference counting overhead. And we see the same in the set intersect of objects benchmark. Again, very, very high arc overhead. So this kind of tells you that when they say use value types rather than reference types, it can have a huge effect, particularly for very esoteric, very focused benchmarks. Now, one of the interesting things is I know there's some work going on in the runtime to try and help with this specific case. So the runtime Swift guys have been looking at the linked list benchmark itself and looking at ways to reduce arc overhead. The option we have really is much more to try and avoid the programming constructs that lead to this. So the next thing we did was we said, OK, we'll work out which is the reference counting overhead, which is everything in gray. And the stuff that's in red is still overhead in the Swift library. So you kind of got the question of what is that red stuff, particularly down here. So you've got a lot of red in, what is that, nopd init and in type flood. So what is costing all of that overhead when you're not actually running your application? So we did the same thing. And what we see here is there's a lot of time in conforms to protocol, stuff around dynamic casting. So this looks like it's where you've got dynamic dispatch going on, probably around checking generics. But it means that there's overheads to other constructs that you can have in your programming language. So anything that really uses protocols or that dynamic dispatch or generics can actually have an overhead at runtime. And what Nick's now going to hopefully talk about is what some of those programming constructs are and things that you might be able to look out for or try to avoid when you're programming. So hopefully we'll be able to switch over without too much pain. Okay.
Bit of a sneak peek, spoiler alert. So this, I find this, oops, sorry. They forced me to do this. They pay my wages. They did allow me to make my own title. So I work for Not on the High Street. I'm a polyglot programmer. I'm, for my sins, actually writing a book on microservices in Go. But I'm a big Swift fan, big advocate. And primarily, I kind of look more at server-side development more so than client-side and apps, and I've done apps in the past, but predominantly that's where my head's at the moment. And it's fascinating, and it's fascinating when you're starting to get into looking at performance things, because one of the things that I deal a lot with is my boss putting the bill for AWS on my desk and saying, "Why is this so expensive?" And I can seriously just do without that, but it's a real cost, right? I mean, when you're running server-side stuff, you bear the cost of the computation. Whereas when you're running it on an app, it's like, it's free. But when you're dealing with huge concurrency as well, so like some of the charts earlier, 40,000 requests per second, then you've got a lot of operations going on there. So thinking about performance and sort of taking a performance focus to the work that you're doing is incredibly important. But that means it's also useful on your apps as well. So I'm going to have to rely on my notes because my brain isn't working right now. But we want to look particularly at protocols because protocols are a big thing. There's a lot of stuff coming out of Apple who are sort of saying, use protocols. Protocols are awesome. Object-oriented is dead, deadish. And I'm a big advocate of protocols. I like writing code by composition. I'm not a massive fan of inheritance, and I don't particularly like overriding methods. And protocols work in my brain. So the key thing is, though, that they're not free. So that there's a very real-world performance overhead and with a protocol. And before we get onto that, I just want to run through a few of the concepts with you. So who knows that the stack is faster than the heap? Right. And do you know why? Does anyone want to volunteer me an answer? No. Yeah. So predominantly that's it, right? So when I look at this, you think, well, if I've got a reference, then actually a reference is a very tiny piece of memory. So that must be really quick to allocate. But it's not. You've got to think of the full life cycle. So the thing is about the stack is the stack as a block of memory, it's there. When you enter a function, it's already there for you. When you create a strut, not a class, then literally the pointer to the end of the stack gets decremented. And when you do it again, it happens again. So in terms of speed and performance, basically all that's happening is you're allocating an integer. It's very fast. Now when you look at the heap, the heap, there's a whole bunch of extra work that's got to go on because the runtime's got to find where it can actually allocate that memory. It's got to search through the heap. It's got to find a hole. It's running multi-threaded, right? So it can't just jump on anything. So you've got to have locking in there and dealing with things like that. And all of that adds up to actually quite a lot slower in terms of operations. And so the stack is definitely faster than the heap. Now reference counting actually has quite a large overhead, and it's maybe not so much the garbage collection or sort of things like that you've got to deal with, but every time you want to increment, you copy an object, there's a level of indirection because you've got to look for the object on the heap. You've got to then update the reference count on that object because the count is actually stored on the object itself on the heap. And again, you've got all of this thread safety stuff going on, right? So you've got to sort of think about that. And then again, we look at why sort of value types are better. Static method dispatch, right? So you call a method internally when it's doing static dispatch, it knows exactly where to go. It points straight at that instruction. Whereas when you've got a class, because you could potentially override that method, the compiler's like, got to keep a reference of where that is. So it's got to store it in a V table, which means that every time you want to call a method, it's got to look up in the table, it's got to get a reference, then it's got to do the call. So there's that level of indirection which can slow things down. And there's various ways of improving that using final and private and all sorts of stuff. And the compiler's actually pretty smart at trying to understand when you've no intention of overriding or creating a level of inheritance, and it'll automatically convert some stuff to static. But that's wow, I've totally gone off that, haven't I? I forgot I had slides. I can put these online. There's useful stuff that I've stolen from the interwebs here. So, I mean, but protocols, right? Protocols adds a new level of pain into this mix, because when you've got two objects which are derived from a protocol, implementing a protocol, then you can't use a vtable because there's no common inheritance. So the system's got to use a protocol witness table, and then that table will exist for every object which implements that protocol, and then that's what you can use to find the direction to the actual implementation. So that can be slow. And then think about arrays, right? What about another level of pain? So I've got two struts. One is say 3 words large. One is 4 words. Now they're of different sizes. So at the runtime, you want to store those in an array, but you've got an array of protocols. Then the runtime wants to keep those buckets in the array of exactly the same size, but it can't do it because you've got a mixture of objects. So what does it do? This is when it's got to go even more indirect, and it has to use a concept of an existential container. And like, seriously, when I'm looking through this and my brain is melting and I'm thinking, please get me out of here. I can do without this, especially today, but it's interesting. And then you start digging into it, and it's really interesting. And the existential container. So this is incredibly intelligent, the way that they've done this. So if you've got a strut, and that strut is smaller than 3 words, then you can put it straight into the existential container, which is great because you're going to save a whole bunch of time, and that'll end up on the stack. Now, if you've got something that's over 3 words, then what you've actually got to do is you might have a strut, but you're going to end up creating that on the heap, because internally it can't store that strut on the stack because there's not enough space. So it'll store it, create the memory on the heap, and then put the reference to the heap into the existential container. That's a strut. So if you do struts which are implementing protocol, they could end up on the heap. So don't assume that they're just going to be straightforward values on the stack. And then you've got a whole nother level of pain. So the reference to the value is stored in the value witness table. And I don't know whether I'm losing the will to live, but there's a reason why I don't write programming languages. So what does the value witness table do? So the value witness table is the thing that understands how to manage the life cycle of your object. So it's dealing with things like the allocation, it's dealing with things like copying references, destroying it, and deallocating the memory. And when you look at how that all works, so this method, this function here, this is what you write. So you have a protocol drawable. You want to call draw, which is a method on that. So you just do that. The compiler the compiler can't just do a direct invocation on that object. It has to do this. So it has to get a reference to the right existential container. It takes a value to the value, a reference to the value witness, to the protocol witness table, sets the type, sets the protocol witness table. It then has to allocate memory copying a reference, so therefore you've got a whole bunch of reference counting stuff going on here. Then it can call your draw, but it can't just call your draw directly because it's then got to pass a reference again to the parameters which are going into draw. And then finally it can destroy everything. So that's an incredible amount of stuff for one method. And I've lost my place again. When you look at performance around this sort of stuff, protocols with small values can fit in the existential container and not in the heap, so they can be quite quick. Obviously, avoiding reference counting is ideal, and dynamic dispatch ends up going through the protocol witness. Protocols with large values are obviously allocated on the heap, and anything goes on the heap is subject to reference counting. That's a lot of stuff around the convenience. So does that mean you shouldn't use protocols? I think the answer is you should absolutely use protocols. And I think it's about being smart about writing your software. It's about being aware of the implications of what you're doing. And the tooling's getting a lot better. And the latest versions of instruments allow you to kind of dig deep into looking at what's actually going on. And Chris sort of showed some of the output from the disassembly, so you can actually see a lot of these extra cores which are getting injected. Generics can be doing something very, very similar. Again, generics are not free; they're not direct. And protocols with generics, well, that's a whole nother topic. So I think before I fall over and pass out, has anybody got any questions? Oh, we only have one mic, but...
If you're doing something time-sensitive, like, say, real-time audio or video processing, would it be best to avoid any sort of polymorphism like protocols in Swift, or even move to C++ instead?
So Swift is incredibly quick as a language because the compiler's got a hell of a lot of optimization in it. I think rather than avoiding premature optimization, I think you can start with a process of just being sensible and being knowledgeable about what you're actually doing. And if you find that the performance isn't suitable because you know the impact of, well, this is a class, therefore it's reference counting, or this is a protocol, you can just slowly start breaking it down. If you sort of get to the end of that and you're left with pretty much nothing but concrete value types, then yeah, maybe you could look at C++, but you won't thank yourself if you do it. I spent...
Well, it's actually one of those things that, on paper, there's no reason why Swift can't perform as well as C++. I mean, in fact, C++ has got some dynamic dispatch in there as well. But yes, in general, if you want to write very high-performing code, you want to avoid dynamic dispatch and polymorphism. But Nick's right when he says don't optimize too soon. There's a general thing of there's rules you should follow. And if you can implement them, then you should. Beyond that, it's always write a benchmark, do some analysis, check that you've got a problem before you start trying to do really difficult things which you probably don't need to. But as the simple benchmarks show, it is possible that you can double the throughput of your application in some cases by making some relatively straightforward changes. So there are some rules that should drop out here, and I think myself and Nick would like to do a bit more work to try and really crystallize what you should do, what you shouldn't do, where and when. But this is just starting to socialize the fact that there are a lot of programming constructs which can have negative side effects. And if you can use instruments or OProfiler, then it's very easy for you to start to find out whether there's small or big gains you can make by changing your application.
Yeah, I think that's absolutely true around a lot of the compiler specializations as well, because I find it personally very difficult to really dig into what they're doing, and they'll tell you some of the stuff at like wwdc and things like that. But there's things around protocols and generics and using rather than having a protocol passing it as a type, but using a generic which conforms and it's kind of locked down to a. Then actually the compiler can look at that and go, well, I'm just going to deconstruct that into a bunch of static method calls. So I think it's definitely an evolving space. Like my number one thing is do not be afraid of protocols. Like use protocols. They're amazing. They'll literally change your life overnight. But the other thing as well is run. If you've got existing apps, run instruments on it. Just do like a CPU profiler and dig through and have a look at the number of reference counting that's going on in there, and sort of just do a little bit of totting up on the CPU. It's quite staggering that the amount that does go on there.
I'm just wondering whether you have the data or not on this Drawable protocol. What the performance implications would be if you had that generically constrained drawable, kind of T constrained to drawable, instead of dealing just with the protocol nakedly, so to speak. Do we know, performance-wise, would that be a big boost or potential?
So yeah, possibly. So if the compiler can actually infer the sort of the usage of that, what it can actually do is it would potentially rewrite everything and create you an inline. So it would, if you had a generic function here, rather than going through all of the stuff that it has to decompose the protocol and going through all of the generics hoops, it would basically just refactor it for you and inline you a static method. So the compiler specializations are getting really good. So one of the key things that Apple always sing on about is basically running whole module optimization on your code base. So that'll run slower, but it'll mean that the compiler can look across multiple files and try and infer the usage better.
Really interesting talk. I mean, I'm not sure I got most of it, but you sort of mentioned this, but I'm not sure if you did. If this drawable protocol had an associated type, what would the performance implications would be?
So if I had an associated type.
So if drawable, would have an associated type, and then your object would conform, would define it. So.
My brain's not working on that one. I'm trying to.
You wouldn't be able to use it as an existential if it has an associated type, so you could only use it as a generic constraint. So this would be a problem.
Yes, so in that case, you'd be calling a known type rather than something that conforms to a protocol. So at that point, everything becomes static. I can link directly to it and so on.
Oh.
What's the state of stability of Katora on Linux?
It's well, I'm going to answer this first because I don't work for IBM and I love it. So we, not on High Street, we've got 2 microservices running Katura in production right now. We're driving real traffic and real money through it. I've never had a problem with it. So I've never been woken up in the 3 or maybe 4 months that we've been running those in prod. And we've been running it in prod since about a couple of weeks before WWDC, so when it was like pretty much in alpha. as a language, and refactoring our code base every week as they change the language in Swift, not in Katura. So yeah, I would say it's ready to roll, but maybe Chris is.
Yeah, so we've been actively lifting it up to the latest version of the language changes in the Swift 3 previews. So on the 27th, those became stable. If you read the mailing lists, according to Tony Parker, the APIs, so Foundation, Package Manager, etc., become stable on August 18th. So from there on afterwards, then we're doing exactly the same thing. It's like we've got a level we can bring up to. That's going to be the last point we need to do stabilization before Swift 3 goes out. Katura can say, here's the final stable version that supports Swift 3, and we don't have to worry about breaking changes every 2 weeks anymore. But yeah, our constant process is get on the latest, make sure it's stable. And once Swift 3 goes out, then there'll be a version that works with Swift 3. And we'll then have a separate version that works with whatever the development driver is.
Just out of interest, with those instances, are you ripping them down and spinning them up again every day, or are you just like leaving them and they're just running solid?
Yeah. So we occasionally will lose. So we're running it inside Docker. It's running on our Mesosphere cluster. We occasionally will lose a container. That's not due to, well, it may be or maybe not due to Katura. It's predominantly not. Mesos will just shift stuff around and kill stuff off as it needs to reallocate resources. But yeah, we've not had a minute of downtime. It's and we're not running like huge numbers. We've got to think of like a 4 container cluster, and yeah, it's been really, really good. I didn't put like a contact, but seriously, if you want to know more, like I can help you out with that. Then just ping me on Twitter or on email or something.
If it helps, we do our benchmarking on an 8-core machine. We do also test it on a 64-core machine. And we do long-run testing up to about 24 hours at the moment, but we know we need to extend that. Our standard processes, long runs should be at least 7 days and ideally a month.
Yeah, so I suppose on that, so we've had containers running for a long, long time. So even during the night when they're not actively getting requests, or they may not be limited, we're hitting the health check endpoints every like 5 or 10 seconds. So that's like an internal check from the orchestration. So literally those containers are getting hit at a very minimum every sort of 10 seconds, and they've been doing so for months, and it's literally been rock solid. Which is obviously a testament to the person who wrote the code, because it's all about the quality of the code, right? Thank you very, very much.
Thanks, everyone.